Thank you for the introduction. On behalf of our group at SIO, I would like to thank the organizers for inviting me to contribute to this session. I will describe a three-dimensional dynamic geodetic datum designed for a landscape with significant crustal motions, such as we face in the Western U.S. This is an issue of importance for the upcoming National Spatial Reference System, requiring special treatment for regions like ours, as well as Alaska and the Caribbean. Maintaining a geodetic reference frame in the Western U.S. is intimately linked with the abundance of frequent natural hazards that we experience. There are two main technologies that we use: continuous GNSS from about 1,200 geodetic quality stations in the Western U.S., providing excellent temporal resolution, and interferometric synthetic aperture radar, InSAR, which provides excellent spatial resolution. Combining the two provides precise images of crustal motions over space and time. To put the dynamic datum into context, currently we use an epic date approach in California. The California Public Resources Code designates the NGS and the California Spatial Reference Center as the two sources of geodetic control in the state. The most recent datum is the California Spatial Reference System, EPIC 2017.50, based on the positions of GNSS stations at that date. For 950 stations, of which 700 provide real-time data streams. EPIC 2017.5 is the sixth in a series of datums, starting with 2000.25 with only 198 stations. A new static datum is motivated by the occurrence of large earthquakes, a significant increase in the number and distribution of stations, and steady tectonic motions. For example, the 2010 magnitude 7.2 El Mayor Cucupa earthquake in northern Baja California displaced all the existing stations in Southern California, necessitating the 2011 epic. Here is the methodology we use to define EPIC 2017.50. Through a combination of two independent analyses of GNSS data by the Jet Propulsion Laboratory, JPL, and SOPAC in ITRF 2014, as realized by the International GNSS Service, we obtained the time series of daily position changes since 1995. Then we performed the time series analysis to estimate the coordinates and 2 sigma uncertainties at that epic date. Next, we transformed the ITRF positions to geodetic coordinates in NAD 83 2011, referred to 2011 10.00 by NGS to conform with the National Spatial Reference System. Finally, we computed orthometric heights by subtracting the geoid heights interpolated from geoid 12B from the ellipsoidal heights. The remainder of my presentation will motivate and describe a dynamic datum to replace the epic date approach. It is built on weekly snapshots of the changing 3D positions of the GNSS stations, allowing users to transform between any two dates. I'll then introduce our SKIP dynamic datum utility for the Western U.S. The first complication in maintaining a datum in the Western U.S. is the steady state tectonic plate motion up to 50 millimeters a year between the North America and Pacific plates across a boundary of a few hundred kilometers in Southern California, with the strike slip San Andreas Fault being the most recognizable feature. Moving to Cascadia up to the Pacific Northwest, and the primary motions are the subduction of the oceanic Juan de Fuca plate beneath North America. The steady movements of any GNSS station can be represented by a single velocity, as shown on the maps. Note the location of the summer 2019 Ridgecrest earthquakes in the right-hand figure here, as I'll be using them as an example. There are also transient motions in all three dimensions that must be considered. Earthquakes can cause sudden offsets up to several meters and long periods of post-seismic decay lasting up to several years until the crust returns to its steady interseismic tectonic rates. Another consideration is significant subsidence and uplift due to groundwater extraction, oil exploration, and volcanism. The rationale for publishing a new epoch date every few years are events such as the July 2019 Ridgecrest earthquakes, which permanently displaced about 250 stations shown on the map by green circles, from 0.016 to 1.93 feet. To take this into account, we introduce new epoch date coordinates for the affected stations at epoch 2019.55. Other processes affected the vertical, including wide areas of subsidence in the San Joaquin Valley. The rationale for the dynamic datum is to avoid having to periodically update coordinates of the reference stations, rather to use the coordinates at the date of the survey and then provide a correction to transform them back to an earlier epoch. As an example, here's an image from GNSS and InSAR measurements showing uplift of up to 47 millimeters a year in the San Gabriel Valley in Southern California due to aquifer recharge, causing outward horizontal motions at the GNSS stations. To motivate the dynamic data approach, I'll show several examples of daily displacement time series for two stations in the Western U.S. The east component time series, shown here, contains the steady tectonic motion of the first station, punctuated by sudden offsets due to 3 earthquakes. Note that the data set contains 2 jumps that are artifacts due to antenna changes, which we have corrected for. After rigorous quality control described in the slide, the final time series are then assumed to represent purely physical processes. Quality control procedures ensure robustness, precision, and accuracy of the station displacements, which of course underlie the definition and maintenance of the reference frame. A parametric fit to the QC time series shown here in the detrended east and up components include, again, 2 offsets due to the antenna changes, coseismic offsets, post-seismic motion after the Ridgecrest earthquakes, and annual and semi-annual terms. The horizontal RMS is of order 1 millimeter and 3 to 4 millimeters in the vertical for a sample of 6,100 data points since 2003. This video describes the accumulating horizontal transient motions that are identifiable in California and Nevada from 2010 to 2019 based on weekly displacement time series. These are motions over and above the steady tectonic motions predicted from the geophysical fault model of Zhang and Shen 2007 that we use for the Western U.S. They include post-seismic decay for 4 earthquakes, most pronounced by the 2010 magnitude 7.2 event in northern Baja California. Result of inflation of the Long Valley caldera and Lassen Peak. We also find some differences between the observations and the geophysical model. We use the model to account for elastic deformation in the crust as stresses build up across locked geologic faults. Here are the cumulative transient motions and their sources at the end of this period. I'd like to focus now on the vertical component. As there is no adequate vertical model available in this complex region, we do not use one. So our datum definition will be solely dependent on the displacement time series themselves. Here are the east and up displacements of a station in the San Joaquin Valley affected by non-uniform subsidence. Here's the model and detrended east component in the center here that shows an offset due to the Ridgecrest earthquakes, but also transient horizontal motions that correlate with the changing rates of subsidence shown on the graph to the right. The subsidence varies and reflects 3 different periods. The first is the normal subsidence rate at this location, a little bit more than 1 inch a year. The second represents the acceleration by a factor of 3 to 4 due to drought, when more groundwater is is withdrawn primarily for agriculture. At the end of the drought, the rate decelerates. This behavior is not uniform across the whole valley, so that the increased spatial resolution provided by InSAR is important. Of course, fitting a single rate to the up component is inappropriate. As shown in the plot to the right, it would introduce an error of up to 0.16 meters or half a foot. This slide shows the accumulation of vertical displacements from 2010 to the middle of 2020. These are due to volcanism, subsidence due to groundwater extraction, drought, and tectonic motion. So let's put all this together. Every week, 3 grids, one for each component, are created by the CSRC from the daily displacement time series. For the horizontal components, we sum the displacements predicted by the geophysical model and the observed transient motions to get the dynamic data grid for that week. The vertical grids are shown in the next, was shown in the next slide. The dynamic datum allows users to calculate coordinates at any epoch of time, and the change in coordinates between any 2 epochs, as illustrated here by the horizontal grids at 4 different epochs. Here are the displacement grids in 3 dimensions at August 20th, 2021, showing accumulated motion since January 1st, 2010, interpolated from the changing positions of the GNSS stations. Note the transients due to the Ridgecrest earthquakes and subsidence in the Central Valley atop the steady tectonic motions. We are working to integrate GNSS and InSAR to increase spatial resolution. Here are some preliminary results. On the left is post-seismic motion 48 days after the 2019 Ridgecrest earthquakes, and on the right, subsidence in the San Joaquin Valley due to oil and gas extraction and groundwater pumping from 2014 to 2019. One of the limitations of InSAR is that the motions are measured in the line of sight of the satellite. GNSS provides a 3rd dimension and a well-defined reference frame. Future InSAR satellites, such as NISAR, will further enhance InSAR GNSS integration. I'm going to demonstrate for you now our dynamic datum utility for the Western U.S. Just 1 second. Here's the interface for the dynamic datum utility for the Western U.S. called SCIP. For demonstration purposes, I've chosen a random location on the map within the region spanned by the GNSS stations indicated by blue dots. The coordinates are transferred to the menu on the left. I keep the input datum as WGS84, which are geodetic coordinates derived from ITRF 2014 using WGS84 ellipsoid parameters, and change the output datum to NAD83 2011. I leave the calendar date as the date format and degrees, minutes, seconds for latitude and longitude. And I've entered feet as the height unit. Once all is set, after I've input the start time and the end time, I just press the Get Coordinate button. Now, scrolling down, we see the input information, the NAD83 coordinates at the output epoch, right here, and the north and east up corrections in feet, along with their uncertainties. to show you the underlying weekly displacement grids. I'll scroll back up here. I'll get rid of the station so you can see clearly. And I'll use a time bar to play the weekly displacement grids. First, in the north component, do that right now. There's a datum north. I'm going to bring the time bar to the start and then scroll through to the current epoch. So at the end of this period, you have the accumulated displacements, including steady state and transient motions. For example, here you see the effect of the 2019 Ridgecrest earthquakes. Next, I can show the vertical component. Bring it back to the start. Let me just set it correctly. And now as I scroll through the time bar, I can see the vertical displacement grids and see how the vertical is increasing in time. We also have the option of entering a list of points. So here. And here are then examples of how to create an input file so that you can do this same operation for a group of stations. So that's the end of the demonstration. I'd like to thank you for your attention and welcome any questions. Thank you.